again, was bizarrely reluctant to talk about his breakthrough. He continually deflected questions about his potentially career-defining discovery. The Berkeley team is perplexed at this point. They rerun their own experiments in spring of 2000. They can't reproduce the event either. This is a problem now. Assuming this... Out of the 218 total winners, only 4 women have ever won the Nobel Prize in Physics. The first was Marie Curie all the way back in the ceremony's 3rd year, for her studies of radiation. She would be the only woman to hold this title for nearly 60 years. Enrico Fermi may just be the luckiest man to ever win a Nobel Prize. Fermi is Italy's top physicist. At the age of just 24, he had been made a professor at the University of Rome, and thanks to his commanding presence, his researchers had nicknamed him the Pope. Unlike the Pope, though, he was broke. Italy's dominance in science had long fallen off since the days of Galileo. If they needed a piece of equipment, they built it from homemade scraps. If they needed protection from radiation, they would sprint back and forth down the hall to avoid getting a lethal dose of whatever chemical concoction they had just made. You see, they were trying to do the unthinkable. They were trying to create a new element. The periodic table back in Fermi's time looked a little like this. Similar to what you're familiar with, but with a lot of pieces missing. You'll notice a few gaps in the middle regions, specifically elements like technetium, francium, astatine, and promethium. But the biggest missing piece is at the bottom. We're missing like a full row and a half. What you see here right now are all the chemical elements that humans had found in nature. Just sitting around in the atmosphere as gases, in the ground in rocks, even a couple liquids. Many of them are stable. A good number of them are safe, so long as you don't eat, inhale, or drink them. A decent portion, however, are not, and are in fact quite dangerous. Radioactive samples that are firing off millions of invisible electrons that can penetrate into your bloodstream. Radium, discovered by Marie Curie, almost certainly killed her. Her daughter, Irene, very likely died in exposure to polonium, the other element discovered by her mother. So maybe you understand now why Fermi didn't mind having to sprint up and down his lab if it meant extending his lifespan by a few years. So how does one go about creating a new element? Well, on paper, it's simple. Add or remove protons. Hydrogen has 1 proton, helium 2, lithium 3. And if you keep doing this, counting all the way up the periodic table, you'd eventually get to the heaviest element in the known world up to that point. Element 90.
Game! One more game!
As uranium.
One more game!
One
more game!
An element is
game!
one
One more
by
game!
its proton.
One more game! One more game!
Vary. That neutron number makes certain elements more stable than others. Carbon-12, with 6 protons and 6 neutrons, is extremely stable. It will stay in that form untouched for billions of years. Carbon-14, with 6 protons and 8 neutrons, is radioactive. It's got an energy imbalance that is actually rectified, and at random it will convert one of its extra neutrons into a proton, and fire off a dangerous electron to account for that energy imbalance. We call this beta minus decay, and what you're left with is an element with 1 extra proton. That's 7, aka nitrogen. Look at that! Purely by adding too many neutrons, the carbon can be stabilized and transformed into an entirely different element. Fermi's idea was to go to the furthest edge of the periodic table, uranium. Element 92, and fire neutrons at it to try and artificially induce beta decay. If it worked, you'd be upgrading element 92 into 93, and if you could do it twice in a row, possibly even 94. Here's a fun problem though. How do you even know if you've created a new element? After all, you don't know what it looks like or what its chemical properties are. In this case, Fermi and his team had to rule things out by verifying which elements they hadn't created. They compared the result with the history of all known elements down to lead, element 82, and couldn't find a single match. Unstable elements often lead to something called an alpha decay. That's when a nucleus spits out 2 protons and 2 neutrons. It leads to a leapfrog effect, where element 94 turns into element 92, then 90, 88, and so on, until they reach a stable element, which is often lead. The other possibility was that they had succeeded. They had made elements 93 and 94 for the very first time. The discovery catapulted Fermi into overnight fame. He was Italy's pride and joy, and obviously, he got first dibs on naming those 2 elements, although he was under a lot of pressure to name the element after a symbol of ancient Rome, fascisium, from the word fasces. Recently, however, the symbol had taken on an entirely new and terrifying meaning. It was the symbol of fascism, and the man pushing for the name was none other than Benito Mussolini. Yeah, Fermi did not follow this suggestion. 4 years go by. It is November 10th, 1938. Two things happen that day. In Germany, it's the night of broken glass. In Italy, a wave of anti-Semitic laws are introduced. Fermi's wife Laura was Jewish, and her passport was on the edge of being revoked. So when the phone call came in that day at 6 p.m. that Enrico Fermi had won the Nobel Prize in Physics, their family didn't think twice. Fermi, his wife, and his children packed their bags and immediately traveled to Sweden. They did not return to Italy, and instead settled in the United States. And almost immediately after they arrived there, Fermi got the news. He had been wrong. He hadn't created elements 93 and 94. He had done something much crazier. He had made an atom explode. When Fermi declared that he had made new elements, he did so because the chemical properties didn't match up with anything as light as lead. Turns out, he should have looked even lighter. A group in Berlin had repeated his experiment, and they saw something really unexpected. They were seeing krypton and barium, two elements that were far too light to be the result of an alpha decay chain. But if you add up their proton numbers, 36 and 56, you get 92, uranium. Fermi had split an atom into two, a process that releases an absurd amount of energy. In reality, Fermi had discovered nuclear fission, a discovery that would go on to fundamentally reshape the upcoming war that he had just fled from, a discovery that would go on to dictate a global power struggle that would last for half a century. Entirely by accident, Fermi had falsely claimed the discovery of two new elements, and half a century later, one man would make a similar false claim, but entirely on purpose. This is a story about Victor Ninov and the race to the periodic table. I gotta show you something. This is the periodic table. I'm betting you recognize it, but it doesn't show the whole picture. Each element has a unique number of protons, but each element can have any number of neutrons. We call these nuclides. Some are more stable than others. There are dozens of elements, but there are thousands of Here's what you're looking at. The x-axis is the number of neutrons. The y-axis is the number of protons. Each square is a possible nucleus. This is hydrogen, exactly 1 proton. This is helium, 2 protons, 2 neutrons. Every possible proton-neutron combination that has ever been observed is present on this chart. Every time we go up a row, that's a new element. I don't think my audience has a lot of overlap with football fans, but if it does for some weird reason, think of this as scoregami, but for chemistry. A checklist where we mark things off that didn't exist before and maybe never will again. See, inside a nucleus is a pair of competing forces. On the one hand, you have the strong nuclear force. At extremely short ranges, it is able to glue together protons and neutrons into bundles. But on the other hand, you have the repulsive electromagnetic force. Protons all have a positive charge, and thus want to push each other apart. Only when the strong nuclear force can overcome the electromagnetic force can you have a stable nuclei. The neutrons, which are electrically neutral, serve as a kind of packing material. Because they don't repel each other, they can act as a buffer for the protons, making a nuclei more stable. Notably, the same element can have different numbers of neutrons, with some being very stable and some decaying immediately. We can actually see those stable nuclei quite clearly. They are the tall pillars in brown. The height on this chart represents the half-life of a given nuclei. A single half-life is the time it takes for a sample to be reduced by 50%. The taller it is, the more stable it is. One thing you can see is that for the lightest elements, the most stable combinations are those where the proton number equals the neutron number. See this line? Perfectly balanced. You can trace this line from hydrogen up until about calcium, and then the trend starts to diverge. For most elements, it's actually more stable to have more neutrons than you have protons. If we follow the path all the way up, we end up at lead. This is the path of stability. As soon as you stray even a little bit from that path, you plunge into the realm of radioactivity. The red pillars here are essentially stable, with half-lives in the billions of years. But by the time you make it to the oranges, you have a half-life in the minutes. A couple hours go by and a sample could be reduced to nothing. And if you touch the water, in blue, those half-lives are in the seconds. And the deep blue, well, that's milliseconds. Or in the worst cases, the half-life is so short we can't even measure it. For some of these nuclei, there's a good chance there's only ever been one of them in existence in the entire universe. A nuclei so unstable, it could never occur on its own, but we forced it to. The beauty of this chart to me is that it's almost like a topological map of our journey through the periodic table. Like a mountainous peninsula surrounded by a raging sea of radioactivity. The sea even has tides. Way up here in this chasm, you'll often get swept away in an alpha decay chain. That's when an element spits out 2 protons and 2 neutrons. It moves 2 spaces diagonally downwards, like this. A cascade that doesn't stop until you reach a stable element. On the south side of the mountain pass, there's a different type of tide. Fermi's beta-minus decay. You lose a neutron, but gain a proton, like this. If you're smart, you can use this to go up a step, potentially creating a new element. But on the other hand, to the northern side of the mountain pass, there's beta-plus decay. You lose a proton, but gain a neutron. No matter where you are, however, every part of this sea is fighting you. The tides of radiation always lead you back to the same place. No matter where you started, eventually you get pushed back to shore, to the main path of stable nuclei. Some people refuse to accept this. They push back, trying to explore more of the sea and potentially uncover more and more land. Enrico Fermi was one of the first. Fermi began his journey here, and he made it as far as the uranium chasm. Over the course of the next 50 years, several different labs would make the same pilgrimage up this mountain, and every new pilgrimage would fill up more and more of this chart. The protagonist of our story, the intrepid Viktor Ninov, claimed he had made it up to here. It's pretty far, huh? To meet him, we've got a bit of a journey ahead of us, and we're gonna need some help. To cross this sea, we're going to need a path. Fermi would go on to do important things. His most well-known achievement is building the first nuclear reactor under the stands of a Chicago football team. But he stopped pursuing the hunt for new elements. That chase would be taken up by an entirely new thing. The discovery of the real elementary debris was weirdly uncertain. On the west coast of America at the University of California, Berkeley, American physics was in full go big or go home mode. Berkeley at the time was home to the world's biggest cyclotron, the best tool in the biz for element hunting. A cyclotron is a type of particle accelerator. It uses magnets to rapidly spin charged particles around in circles and then smashes them into targets. Now, this isn't one of the multi-mile rings that you're probably thinking of. Those are actually too powerful for making new elements. For this, you need something a bit more delicate. Berkeley's state-of-the-art tool was 60 inches in diameter, and it could pelt a uranium target with neutrons, again hoping for Fermi's predicted beta decay. And one day, after finding a radioactive lump that matched no known samples, element 93 had officially been confirmed. We now know it as Neptunium. The credit for this discovery went to Edwin McMillan and Phil Abelson, but the celebration was short-lived. Their publication was met with silence from the academic community. No one dared acknowledge the breakthrough, lest it give the Germans any inspiration. Although America hadn't yet joined World War II, they were preparing to, and so Macmillan and the rest of the lab's top scientists were soon drafted into the war effort, working on radar, or in some cases, the Manhattan Project. That left a vacant seat to take over the element hunt. That's where our captain comes in, Glenn Seaborg. As the descendant of Swedish immigrants, they had left their home country with the last name Sjoberg. Upon reaching Ellis Island, an immigration official decided that their new name would actually be Seaborg, and it stayed that way. This customs officer had no idea that his half-assed spelling attempt would one day make it on to the periodic table. Glenn, from a young age, went wherever the tides of life took him. After his family decided to move from icy Michigan to sunny California, an 11-year-old Glenn decided to add an extra N to his name because it looked cool. Can't argue with that, Glenn. And on another day, as a 24-year-old chemistry student strolling through the Berkeley campus, someone from the radiation lab stopped him and asked if he could help them separate out some chemical samples. He was just the first chemist they found on campus. Seaborg would eventually work his way up through the lab, and with Edwin Macmillan gone, he asked if he could take over as the new captain of the element hunt. Although Macmillan never got to try it out, he'd come up with a recipe for element 94, and good old Glenn was going to get the first crack at it. If you add one neutron to uranium, it beta decays into element 93. But say you fired a proton and a neutron. The proton would immediately bump it up into element 93, and then the extra neutron would have a chance at beta decaying, upping it one more time to element 94. It really is like an absurdly delicate game of Jenga. So yeah, that's how you make plutonium. It's safe to say that the discovery of plutonium was kind of a big deal. It's actually an even better fuel for a bomb than uranium, which was the original plan for the Manhattan Project. And thus Seaborg and his team were immediately drafted to Chicago to work with... Oh, hey, it's our old pal Fermi. There they spent months artificially making enough plutonium to flatten a city or two. It was difficult and hazardous work, and at one point a lead brick fell and broke a beaker, and 25% of the world's entire plutonium supply was soaked into a copy of the Chicago Times. But the Manhattan Project is a story that's been told many times by people better equipped to tell it than me. The story we care about involves Glenn Seaborg and Berkeley. By this point, they have enough plutonium for their bomb, so Glenn and his team are free to ponder some other questions. Why stop at 94? Surely the periodic table didn't end at such a weird number. And they didn't even have to reinvent the wheel. Instead of starting with uranium, just start with plutonium and fire neutrons at that. To go back to the Jenga analogy, you're trying to build a taller tower, but the bottom rows are radioactive, and they keep disappearing on you. But as long as you're building the tower faster than it's disappearing, maybe you can find a new element. Now at this point, we're going to pick up the pace a bit. There are still a lot of missing pieces between us and our friend Victor Nino. If you want to read more, I highly recommend the book Super Heavy by Kit Chapman. Essentially though, the timeline went something like this. Element 93, discovered by Berkeley. Element 94, Berkeley. Element 96, discovered by Berkeley members in Chicago. Element 95, Berkeley members in Chicago. 2 atomic bombs are then dropped on Hiroshima and Nagasaki, killing upwards of 250,000 in the immediate blast, poisoning the ground and air for decades after. Next up was element 97, once again found by Berkeley, and since they definitely earned it at this point, they named it Berkelium. Element 98, hey, guess what? It's Berkeley again. They named it Californium this time. With 4 elements in a row, the New York Times joked that they should have just gone with Universitium, Ovium, Californium, Berkelium. It was at this point that the Nobel Academy finally acknowledged Berkeley's achievements, and so Edwin Macmillan and Glenn Seaborg shared the Nobel Prize in Chemistry. Next up was elements 99 and 100, and this is going to sound extremely stupid. I swear I'm not making this up. America dropped a nuclear bomb in the middle of the Pacific Ocean, sent fighter jets through the very, very top of the mushroom cloud to collect samples, raced like hell to get the rapidly decaying lumps back to Los Alamos in New Mexico, where they were then analyzed to see if they had made any new elements. Yes, and unbelievably, they did. Since Berkeley helped out with the analysis, they were co-credited with the discoveries of 99 and 100. These were named after 2 of the field's greatest minds, Einstein and Fermi. Both of them had passed away just months earlier. And soon enough, there was element 101. Again, found at Berkeley, named to honor the creator of the modern periodic table. It truly was one of the most dominant streaks in science history. Every other lab was nothing but quantity, as Berkeley added half a row to the period. There was nowhere else to go except further and further up. As of 1945, 4 earlier gaps in the table had been filled. Known as 43, 87, 85, and 61. There were more elements out there, but it was going to get harder and harder to find. From this point on, he was come to be known as the super chemist. As for Glenn Seaborg, he was once again going where the tides of life took him. His career took a turn when he received an out-of-the-blue phone call from John F. Kennedy, of all people. He was about to be named the next head of the Atomic Energy Commission. Later, he would become a close confidant of Lyndon B. Johnson, and they were apparently such good friends that Seaborg was regularly invited to the White House to just come hang out and chat. After he had made the fuel for the first atomic bomb, Seaborg would push hard for treaties that would limit the spread of nukes. This is not an attempt to absolve him of his role in that, but I think it's important to fully contextualize it. This is where Seaborg diverges from our story, but Berkeley does not. Every element in the streak from 93 to 101 had been discovered by a team with some sort of tie to Berkeley. From this point on, it would not be so clear-cut, and the controversy would play out on a geopolitical scale. There are a lot of famous Einstein quotes out there, but there is one I saw for the very first time while researching this video. This is what Einstein had to say on the topic of making new elements. It would be like shooting birds at night, in a country with not that many birds. So true, bestie. And he's not wrong. Element hunting is essentially like gambling. The basic setup is easy enough to describe. You have a target, and you have a bullet. Except both the target and the bullet are so small they're invisible, and also the target is almost certainly radioactive. And even if you do make a direct hit, there's a good chance you'll break apart or even destroy parts of your target. So this is less like aiming a gun at a target, and more like a game of roulette with the absolute worst odds imaginable. If you take just one spin, the odds of hitting the exact right pocket are not good. But if you take 5 million spins at the roulette wheel, your odds go from basically impossible to just barely within the realm of possibility. Yeah, the odds are terrible, but sooner or later, you're bound to get a hit. For element hunters, this means aiming a beam at a target and leaving it firing for literal months, which you can imagine gets very, very expensive. Depending on the lab and the type of beam, firing continuously for just one day can cost somewhere in the tens of thousands of dollars. A few months of beam time then is easily in the millions of dollars. We have a lot of uranium on Earth, about 5.5 million metric tons, and even the shortest half-life is still 25,000 years. So getting a large enough uranium target to fire neutrons at isn't really a problem. So making plutonium is easy enough. But then for the next level, your target needs to be plutonium. And then after that, it's curium, Einsteinium, etc. Each time, your target's half-life is getting shorter and shorter. 1 gram of uranium costs about 13 cents. A gram of Einsteinium costs about $27 million. Most casino goers can't afford that kind of buy-in. But, in theory, if you've got unlimited time and unlimited money, element hunting gets a hell of a lot easier. Berkeley, situated in the richest state in the richest country in the world, had the most money and the best equipment, so no wonder they had the leg up. But that's the beauty of the casino. It was just a matter of time until another lab got lucky. While the Americans were busy building a bomb, the Soviets were lagging behind, embarrassingly so. Admittedly, they were very occupied holding off the Germans on the Eastern Front and had focused all of their scientists on metallurgy. The Soviet nuclear program owes its start to one random volunteer lieutenant on the Eastern Front, Georgy Flerov. Prior to the war, he had been following the topic of nuclear fission quite closely, only for all publications to abruptly stop talking about it in 1939 of all years. He found this bizarre, as the ability to harness the power of an atom was like the most exciting thing to come out of physics in decades. He soon connected the dots. Oh my god, they're all making bombs. Flerov, against all conventional wisdom, wrote directly to Stalin and basically demanded that the Soviets devote as many resources as they could to nuclear technology. Flerov was, Surprisingly, not punished for this insubordination, but instead made a key player in the Soviet nuclear program. Following the war, however, Flerov changed his focus. He wanted to hunt elements. He founded JINR in Dubna, a small Russian town. Soon, it would be America versus the USSR in the hunt for elements. Wow, science being used as a tool by rival superpowers to help fight a Cold War? Never heard that one before. Couldn't be me. It's safe to say that nearly every new element from this point on would be hotly contested, and any and all evidence would be denied by either side. These were the Transfermium Wars, and here's how they went down. First, a small lab in Sweden claims they found element 102. No you didn't, says Berkeley. Your equipment is cheap and bad and your tests not thorough enough. I agree, says Dubna, and then they both bullied Sweden until basically nobody believed Sweden had actually found anything. Berkeley tried some experiments of their own, which accidentally caused a radioactive dust spill that resulted in their lab being evacuated, and 27 people had nearly 3 months shaved off their average lifespan.
Just one
Dubna
more
then
game,
swoops
and
in with
that's
even
it!
better results and claims 102 for their own. Then
Come on,
Dubna
let's
claims
play
104,
one more
103,
game!
and 105.
One
So
more
fast, all the
game!
Americans
One
could do
more
was try and
game!
nitpick
One
their
more
data
game!
and make
One
those same
more
elements,
game!
but just.
One more
One
game!
more game.
It didn't help
One
that
more
each side
game!
had
One
their
more
own
game! One more game!
To confirm a new
One more
element, the
game!
Soviets
One more
preferred to use
game!
spontaneous
One more
fission.
game!
Their
One more
detector
game!
numbers
One more game!
were
One more game! One more game!
One more game.
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 One more
game.
game!
One more game.
One more game!
One more game. One more game.
One more game!
One more game.
One more game!
One more game.
One more game! One more game!
It's almost as if this sort of cutthroat had struck more sloppy work. Sure hope that doesn't warm back to bite anymore. For now, the element hunt had stalled. By the time you get up to element 102, your half-life is less than an hour. Before, you could rely on other dedicated labs to manufacture you enough of an element. They could ship it to you, and then you could start firing your beams at it. With a half-life of less than an hour, you couldn't even get a sample across town, much less an intercontinental flight. The quantities they were working with were getting smaller and smaller. When Berkeley claimed the discovery for curium, element 98, they did so after generating around 5